Hi guys, welcome to module 3.1 of this Learner Space course on device physics. Hope you guys have enjoyed so far. So in today's module, we're going to talk about density of states, and this is the stepping stone for us to be able to start talking about the concentration of carriers inside the semiconductor, like how many carriers are concentrated at a specific location depending on the doping and other factors. For this, we need to first talk about the density of states. Cool. So, getting into the motivation for why we are like, what is the density of state, why we are interested in calculating it. So, to know the macroscopic properties of a semiconductor, like its conductivity, we need to know the distribution of its electrons in the various bands. Then we can know the number of free carriers. So if I know the number of electrons in the conduction band and the number of electrons in the valence band, correspondingly I'll know the number of holes in the valence band. I will get to know how many free carriers I have available. So once I know that, then properties like the conductivity of the semiconductor I can find out, right? So the motivation is that we want to be able to find out the number of electrons in the various bands. And the way we do this, yeah, I'll get into what all these symbols mean, but we multiply this quantity to delta S by delta E with the occupation probability and integrate that with energy across the limits of the band to get the concentration in that band. Now, what do I mean by this various symbols, right? So what is delta S, right? So if I start from the bottom and name number each state, give each state a serial number, I'll call that serial number S. So delta, so S just denotes which state I am talking about. So delta S, the quantity delta S by delta E is just that if I take some energy difference delta E, how many states delta S are present in that energy difference. So coming to the factor of 2, why we are multiplying 2 here is that each for some state that exists in some energy difference, there are two there are two equivalent states, one which will allow the spin up electron and one which will allow the spin down electron. So that's why we're multiplying by 2, because we want to consider both the possibilities of the electrons for a given given energy level, right? So essentially the 2 is to allow the spin up and spin down, and our delta S by delta E is just the serial number of the state uh, for an energy difference delta E. So if in 0.1 electron volts I have 10 states, then my delta S by delta E will be 100, 10 upon 0.1. So 100 states per EV, and each state has a duplicate state which will allow the opposite spin of the electron. That's why you multiply by 2. So essentially what that means is that I can fill in 200 electrons per EV, per electron volt, or per any unit of energy, 200 electrons per joule. So what that is telling me, when I will when I will multiply this by the occupation probability, so if I have available space for 200 electrons per joule and say I have an occupation probability of 50%, that means that I will have 100 electrons per joule. And if I will integrate this from the limits of the energy, if I will integrate this with the limits of the energy, say my band goes from 0 joules to 100 joules. So if I will integrate the quantity 200 electrons per joule from 0 joules to 100 joules, what I will get is that I have 200 electrons in the band, right? So this is the technique that we are going to try and use to find out how many electrons are there in the band. Now, so this quantity 2 delta S by delta E is what we actually calling the density of states. Now, you might be wondering that if we are trying to set up an integral like this using delta S by delta E, why are we using delta and not D? Like, why are we not saying ds by dE? Because essentially, we are taking the derivative, right? So the issue with using the notation D is that these energy levels are discrete. So we cannot use continuous notation for discrete quantities. So even if they're really close, you can only use the symbol D for things that are infinitesimally close apart. So we are using delta, but the idea is still that when we are doing this delta S by delta E computation, we still want to tend delta to 0, but we won't use the symbol D because it's not a continuous quantity, right? So yeah, just like broad overview on the motivation of what we are trying to do. Cool. So we call this quantity 2 delta S by delta E the density of states, and we basically want to figure out that for some small energy gap delta E, how many electrons are present in this energy gap, and then integrated over the total energy gap, right? So just take some small strip, find out how many electrons there are in this as a function of the energy, and then just integrate over all possible strips. That's what we are doing. To the end goal, I'll reiterate, is to find the number of electrons in a band. So just take a small energy gap in the band, find out the number of electrons in that, and then integrate to find out for the whole band, right? Now, I'll just again reiterate, how do we find the number of electrons in this band delta E? So we can divide this problem into few parts. Firstly, how many energy states are present in this delta E? Secondly, how many electrons are in each occupied state? Or like how many duplicate states do we have? Which is where we get the factor of 2 from, because we can have spin up electron and spin down electron in the same state. So these first two quantities we have clubbed together as 2 delta S by delta E. And then when we consider how many percentage of states are occupied and we multiply by that, then that product will give us the answer of how many electrons are present in this gap delta E. So again, the occupation probability or the percentage that are occupied is something that we saw in the previous module how to calculate already. So density of states, which is this 2 delta S by delta E, is actually answering the product of the first two parts, which is these two parts. So that is what we are getting into. So I hope it's clear what density of state means, and if it is, we can move on to how we will calculate it. Alright, cool. So let's move into the calculation of the density of states. We know that we want to ultimately calculate 2 delta S by delta E. We can break this up into calculating delta S by delta K and delta K by delta E. So the motivation to do this is that if you will go back to one of the previous modules, we already established a relationship between E and K, which even if you've forgotten it is okay. I'll bring it up in one of the upcoming slides. But since we already know a relationship between A and K, we can easily calculate this quantity. So then if we are able to calculate delta S by delta K, our problem is solved, right? So uh, again, let me like bring you back to what exactly K is. So we spoke about K being the wave vector in one of the previous modules, and we spoke about how for each K you have each K that solves the Schrodinger's equation in the form of e power iota kx, you have a corresponding energy eigenvalue E. And so, yeah, that was the interpretation of K. And we also spoke about how K relates the wave nature as well as the momentum of the particle, right? So, yeah, so we want to essentially calculate now this quantity delta S by delta K. Now, for the calculation that we'll do after this, it like we are going to use a particular like geometric or mathematical abstraction that is important to understand. So the math will flow regardless, but to be able to visualize it, you'll need to be able to visualize this abstraction that I'm telling you about now. So you need to imagine that there exists a lattice in 3 dimensions, and normally you assume that in lattice you are talking about the distance, like distance between 2 points is difference in how far they are. It's in units of position, right? So if you're imagining a regular lattice, you'll think, oh, every point in the lattice is 1 centimeter apart. Now, instead of imagining this difference being in units of position, I want you to imagine a lattice where the difference is in units of k, where k is the wave vector, and we will call this new type of lattice a reciprocal lattice. And I want you to imagine this just like any other simple cubic lattice structure in 3 dimensions. So what we are essentially doing is that rather than making a lattice in the real space, we are making a lattice in k space. So where we had the distance between 2 points be real number, now they are expressed in differences in values of k. And as you already seen in the previous module, k is quantized by this 2 pi by a, where distance between subsequent values of k takes this value 2 pi by a, right? So what that essentially means is that we are constructing this reciprocal lattice in k space, right? Uh, so now when we want, so I just want that you are convinced that we can make this kind of geometric or mathematical abstraction. Instead of just instead of having real number distances between points in real space, we are constructing a new type of space, which we call the K space. And we are constructing this lattice in this space where instead of having uh, distances in real numbers, we have distances in k. And like, I'll just apologize, this is an error. The distance between 2 points is not 2 pi by a, it's 2 pi by na. You can, where capital N is the total number of lattice points, you can go back to the previous module for the derivation of that. Cool. So of course, if you have any doubts in any of this, you can always reach out to me. uh, Delta S by delta K is the number of states in the values K and K plus delta K. So if I have delta S states in the values between K and K plus delta K, that will be the value of my delta S by delta K, which is what I want to calculate. So yeah, I just want to first draw your attention to what mathematical abstraction we are going to be using. So it's just a 3D lattice in K space. Cool. So we can move on with the calculation now of delta S by delta K. Cool. So now we want to calculate delta S by delta K. So for that, what we are going to first do is talk about what is the, in this new lattice in K space, what is the volume occupied by one K state in 3 dimensions. And what I'm going to claim is that this is just the cube of the distance between any two states. So it's just 2 pi by L cubed, where L is the total length of the lattice, for example. Now, because I know that N times A is L, right? So, because there are N atoms and the spacing between each atom is A, the distance between any two K states is 2 pi by Na. And the claim is that the volume occupied by any one K state is just this cube. Now, why this works is that I want to bring you to this visualization, right? Now, this is just a cube with side length 2 pi by Na, right? Because it's the distance between two corresponding points in the lattice, and that distance is 2 pi by Na, and this is just a cube of that distance. So this is just the volume of the cube is just the cube of the length of the side. Now, how many atoms are there in this volume, right? Or how many spheres actually occupy this volume? This is something you would have seen in solid state in chemistry. So the idea is that each sphere is 1 by 8 inside this particular cube, and you have 8 such spheres. So net you have one sphere inside this cube, which means you have one K state inside this cube, which means the volume of this cube is exactly that which is occupied by one K state, because inside this you have exactly one K state. So this is how we are justifying that the volume occupied by one K state is this 2 pi by L whole cube. Now, the way we of course want to bring in delta S by delta K, right? So now the number of K states in some K space volume V is of course V by delta K, right? So if one state occupies one cubic meter, for example, and I have 1000 cubic meters, I'll know that the number of states inside that is 1000, which is exactly what I want, this relationship between delta S and delta K. Now, of course, this is read as del because I want, this symbol is read as del because I want to use, I've already used delta for something else. So the idea is that we've already figured out how much volume one K state occupies. We just need to find out that in this K space K and K plus delta K, how many states are there, right? So, how much volume is there? Because if we divide that by the volume occupied by a single state, we can find out how many states are there. So, if we have this K and K plus delta K distance, and we want to find out the volume that is occupied by that distance, assuming delta K is small, we know that K is a wave vector in 3 dimensions. So delta K can point in any direction. So this is just like you have a sphere of radius K, and you're asking how much is the volume that is occupied by delta K more than that. So you can just multiply the surface area of that sphere 4 pi K square with delta K. Assuming delta K is small, this approximation will hold. So in this range of K and K plus delta K, you have this much volume 4 pi K square delta K, and each K state occupies this much volume 2 pi by L whole cube, which means that the total number of states in this range K and K plus delta K is given by this divided by this, because this is the total volume and this is the volume taken by one state, which gives us this relation that the total number of states delta S is K square by 2 pi square times delta K, using which we can get our delta S by delta K, which is what we had set out to do, right? So this might be a bit difficult. So if you've not understood it, just think about it, maybe go back, watch it again, and let me know if you have any doubts, right? Cool. So again, this is how we are planning to calculate 2 delta S by delta E. We're going to multiply 2 by delta S by delta K and multiply that by delta K by delta E. Now, delta S by delta K is what we already calculated on the last slide. We have this EK relationship again, E equal to EC plus H square K square by 8 pi square M. I kind of gave you a classical gut check of this by talking about the sum of kinetic energy and potential energy. We had seen it in a previous module. We can just differentiate this relation and get delta K by delta E in terms of energy, right? So I will leave that calculation or the justification of that calculation to you. But the point is that it's something that you can do, and then just multiply that with what we got in the previous slide for delta S by delta K. And when you put it all together, you will get this expression root 2 by pi square m by h bar square. I'll just note for you that h bar is commonly used symbol of h upon 2 pi. So if you ever encounter the symbol h bar, it's h upon 2 pi. So this whole thing power 3 by 2 root of, when you do this calculation, you will get square root of e. Now, just like in some of the previous calculation where we got some value of E and we a value in terms of E, and we said that this holds as long as your distribution is centered at the origin, and then we introduce the shift of origin with the Fermi level. We did that in a previous module. Similar thing is applicable over here, which is that the formula where you'll have root of E over here in the density of states, that will hold when your minimum energy in the conduction band is 0. But when we are solving for some, like when you don't have your origin of your energy at the conduction band, you have your origin somewhere else, you need to have this shift of origin with respect to the lowest point of the conduction band. So we have a shift of origin to EC, where EC is the lowest point of the conduction band, and therefore we get this like complete density of states for the conduction band, which is this whole expression. Now again, reiterating the motivation for doing all of this was basically just that now if you'll multiply this with the occupation probability and integrate it over the limits of the conduction band, you'll get the total carrier concentration or number of electrons in this conduction band, which is what we set out to do, right? So this is the expression you finally derive for density of states. Cool. So what is the key takeaways in this module? Firstly, the product of the density of states and the occupation probability integrated with the energy gives us the concentration of electrons in a given band. We imagined the conduction band, but similar can be applicable to other bands as well. Secondly, while doing the calculation of density of states, we imagined a reciprocal lattice in K space rather than imagining geometry in real space where you have X, Y, and Z. You can just as easily imagine a geometry in space of some other variable like K space, which is what we did in this question. So the rules of geometry are applicable irrespective of whether you're talking about distances in meters or you're talking about differences of values of k. So it just so happens that in the real world, most applications of geometry are used for Cartesian distances, but it's not necessary that the reach of geometry is limited to that. And finally, we use this reciprocal lattice to do the calculations and finally get this density of states. Now, finally, in the next module, we are going to use this density of states and the occupation probability, which we calculated in the last module, to calculate carrier concentrations, which is something that we've been trying to get at since quite some while now. Hope you enjoyed this. See you in the next module.